Good morning. Today we will continue with studying the flapping motion, in this case with the fuselage translation and rotation. If you remember, we derived the flapping equation of motion when the helicopter was having only a pitch motion q and it was fixed to the ground. You remember that we had to introduce the Coriolis effect and that pitch rate had also an aerodynamic effect on the motion. We have transformed the rotating motion to the steady motion or the distilled motion using the Fourier transformation, and we finally obtained that in the non-rotating system, the flapping motion is composed of a coning angle, of a longitudinal disk tilt, and the lateral disk tilt. We also proved that the flapping motion is damping the fuselage motion, as the signs of these terms are negative, opposing to the pitch rate. Now, consider that we are having the fuselage free, and we are translating with a velocity v, and the helicopter is rotating with a pitch rate q. The equation of motion that we should start is, of course, again a second order differential equation for the flapping motion. The Coriolis term should be introduced. The only difference when we are having the fuselage translating is that we have different aerodynamic forces which will produce different aerodynamic moments. What is the aerodynamic moment on the blade element? We go back on the blade element and recall what are the velocities of the profile. The velocity, advancing velocity, v cosine of alpha c, remember that we are in a control plane, can be decomposed in a velocity along the blade and perpendicular to the blade element. These velocities will have their perpendicular and translation components. So the component which is in the plate of the motion is the tip of the tip velocity omega r plus v cosine alpha c sinus c. So it is this term. Perpendicular to the blade we have, of course, the induced velocity, beta dot r, which is the flapping velocity, the v sinus of alpha c, which is the component which is in this plane of the helicopter, which is coming into the plane of motion, the pitch rate, and the component v cosine of alpha c cosine of c, which is due to the flapping motion having its own component v cosine of alpha c cosine c sinus beta. This is, if you understood, immediately the angle of attack. Theta minus the inflow angle, but now the inflow angle is a tangent of all these velocities. What is the interpretation of the aerodynamic flapping moment contribution? It follows that if there is an excitation beta dot, there will be a change in the angle of attack delta alpha, which is having a change in producing a change in lift forces, which is also changing the aerodynamic moment. Usually, the aerodynamic forces have the character of a damping term in the flapping equation. Compared with hover in forward flight, you see that this dependency is also is varying according to the azimuth angle c. However, averaged over one revolution, the mean damping is the same as in the hovering flight. In forward flight, the dominating excitation of the blade flapping is actually the asymmetry of the flow which is encountered by a blade due to the advancing velocity. Further, the aerodynamic moment can be now further calculated as an integral along the whole blade from the lift force on every blade element. But now the angle of attack we have derived it, and the velocity on the blade tangential is of course this component. Using non-dimensional notation, the advance ratio and this lambda c, which is the component of the velocity coming perpendicular to the control plane, and the induced velocity non-dimensionalized, we can perform the integral as a function of radius, and the result is, as you see, down. It will be depending on the azimuth angle, and it will have also free coefficients. Now, substituting this aerodynamic moment into the flapping equation of the blade, it leads you to this final equation. The flapping motion is a second order flapping differential equation where the aerodynamic damping is introduced, as you see in the case of the hovering flight, but now there is also a component due to the advancing velocity. And the blade RPM, the natural frequency is almost the one of the RPM, but now there is a centrifugal spring and also an aerodynamic spring. This part corresponds to the free excitation. You see that this excitation is a function of the pitch angle, of the component, perpendicular component of the forward velocity on the control plane, induced velocity, advance ratio, pitch rate. And you see also that this excitation, it's exciting at the natural frequency of the blade, omega. The conclusion is that we have a second order linear differential equation with variable coefficients. We have an excitation in the so-called 1 per revolution, 1p, and 2 per revolution, 2p. And that this equation, it is periodic equation with a periodic frequency. To solve such an equation, we should apply the Floquet theory. You see also that even with a damping in a system, there is a possibility for instability due to this periodicity of the motion. Also, you see that the frequency of the excitation is almost the natural frequency of the blade. Again, the blade is not breaking because the flapping has a high damping in a system. Now, let's transform the motion from the rotating system to the non-rotating system, applying the first order Fourier coefficients into the equation of motion for the forward flight and equalizing the free terms, the terms in cosine psi and the terms in sinus psi. It will lead you to the following distal motion. The coning angle of the blades, you see, is depending on the pitch angle, on the advance ratio, and on the perpendicular component of the velocities, induced velocity and perpendicular component of the velocity. Also, there is a longitudinal disk tilt, which is showing that actually the rotor cone, it will blow back. It has the characteristic of a damping. Here is the longitudinal disk tilt angle, A1, which you see again depends on the pitch rate, advance ratio, on the helicopter pitch, and all these components. So there is a lateral disk tilt. The rotor cone is tilting to the right for a counterclockwise rotating helicopter, and is again depending on the pitch rate and on the pitch angle of attack, advance ratio, lambda c, and A1. So here it was the coning angle substituted. In reality, the lateral tilt is strongly influenced by the non-uniformity of the induced velocity. Remember that we assumed induced velocity constant. Usually, an extra term K prime is adding to the lateral disk tilt, which is having this expression obtained from experimental results. So the lateral disk tilt finally can be calculating using this formula. You will not need this lateral disk tilt angle, and as we will develop only a longitudinal simulation model. But when you go and simulate a 6 degrees of freedom helicopter motion, the rotor motion has to be included, including this lateral disk tilt angle. This will end the lecture of today on flapping motion with fuselage translation and rotation.